Now we'll work for practice 17.6. Find the pH of a 0.0150 molar acetic acid solution. Acetic acid is the component of vinegar that makes it acidic, and this is in fact a weak acid. So let's go ahead and begin by writing the equation for the dissociation of the acid in water. That's HC2H3O2, so that's acetic acid, plus water yields H3O plus the acetate anion, C2H3O2 minus. Remember, the generic equation for this is HA, where we have the H plus and the A minus. This is our anion that goes with the acid, plus water yields H3O plus A minus. Okay, so what we're doing is we're removing the H from the HA, and it leaves behind A minus. Remember, this is our acid, and this is our conjugate base of the acid. Water in this case is acting as a base, and H3O plus would be the conjugate acid of water. Okay, so this is the generic equation, so we can use that generic equation to write the dissociation of all of our weak acid problems where we have a monoprotic acid. So we've written the dissociation equation for our acid, and now we want to prepare an ice table. That stands for initial, change, and equilibrium. That's why we prepare an ice table, to determine the concentrations of our species at equilibrium. And if we can't determine those concentrations through direct calculations, because we have values for that, we use X to represent the dissociation. So we're beginning with 0.0150 molar of the acetic acid, and essentially none of the hydronium and none of the acetate. We're losing X of our acetic acid and gaining X of the hydronium and X of the acetate. So at equilibrium we'll have 0.0150 minus X of the acid. We'll have X of the hydronium and X of the acetate. So again, I stands for initial, change, and equilibrium. Initially, we have the top row. Our change is represented in terms of X, and at equilibrium, we'll have these amounts of each species. And we can find out what X is by setting our products over reactants equal to the K for the acid. So let's set up our Ka expression. Ka is equal to products over reactants at equilibrium. So remember, we don't count the water because it's a liquid. So we have hydronium times acetate over acetic acid. And where do we get the Ka from? We can look that up in a table. So the Ka for acetic acid is equal to 1.8 times 10 to the minus fifth, and that in each of our species on the top is equal to X, so that gives us X squared on top divided by 0.0150 minus X. So that's equal to X squared over 0.0150 minus X, and if we assume X is small, okay, then we can set up this expression as 1.8 times 10 to the minus fifth equals X squared over 0.0150. So we multiply both sides by 0.0150 and then take the square root of both sides. So X is equal to the square root of 1.8 times 10 to the minus fifth, okay, times 0.0150 divided by, and so X is equal to 5.196 times 10 to the minus 4. So X represents our hydronium ion concentration. Remember from our equilibrium expression, X is the hydronium ion concentration, and it also represents the acetate concentration at equilibrium. But we don't care about the acetate. We only need the hydronium in this case because we need to be able to calculate the pH. So that's equal to 5.196 times 10 to minus 4. Okay, and so the pH is equal to negative log of H3O plus, which is equal to the negative log of 5.196 times 10 to minus 4, which is equal to 3.28.